Have you ever wondered what the universe is truly made of at its most fundamental level? For decades, physicists have been on a quest for a theory of everything, and a key tool in this search is something called the action principle. Today, we're going on a deep dive into the world of theoretical physics to explore four monumental actions: the Nambu-Goto, Polyakov, Einstein-Hilbert, and the more recent General Obidi Action from the Theory of Entropicity. Get ready, because we're about to journey to the very fabric of reality. Let's start with string theory. Imagine a subatomic particle, not as a point, but as a tiny, vibrating one-dimensional string. As this string moves through spacetime, it traces out a two-dimensional surface called a worldsheet. The Nambu-Goto action, proposed in the 1970s, was the first attempt to describe the dynamics of this string. It's elegantly simple. The action is directly proportional to the area of the worldsheet. Think of it like a soap film stretching to minimize its surface area. The Nambu-Goto action says that a string moves in a way that minimizes its worldsheet area. This principle is beautiful, but it comes with a mathematical headache, a pesky square root in its formula that makes it notoriously difficult to work with, especially when we try to quantize it. This is where the Polyakov action comes to the rescue. Alexander Polyakov found a brilliant way around the Nambu-Goto action's problems. Instead of dealing with the worldsheet area directly, he introduced an auxiliary field, a sort of mathematical scaffold, called the worldsheet metric. This new metric describes the geometry of the worldsheet itself. The Polyakov action looks a bit more complicated at first, but it has a massive advantage. It gets rid of that nasty square root. The formula becomes a quadratic one, which is much easier for physicists to quantize. It's like trading a complex, clunky tool for a sleek, versatile one. By introducing this new metric, the Polyakov action not only simplifies the math, but also reveals deep asymmetries, making it the preferred starting point for most modern string theorists. At the classical level, it's equivalent to the Nambu-Goto action, but in the quantum level, it's a game changer. Now, let's shift our focus from the tiny string to the grand scale of the cosmos. How do we describe gravity in the very shape of space-time? This is the domain of Albert Einstein's general relativity, and its cornerstone is the Einstein-Hilbert action, proposed by David Hilbert just days before Einstein published his final field equations. This action describes the dynamics of space-time itself. It's remarkably concise. The action is essentially the integral of something called the Ricci scalar curvature over all of space. What does that mean? The Ricci scalar, or R, is a number at each point in spacetime that tells us how curved it is. The Einstein-Hilbert action says that spacetime will bend and shape itself to minimize this tilting curvature, given the presence of matter and energy. By applying the principle of least action to this formula, we can derive the famous Einstein-Hilbert equations, which tell us how matter curves spacetime, and how that curvature dictates the motion of matter. It's the action that gives us black holes, gravitational waves, and the expansion of the universe. It's the mathematical art of our modern understanding of gravity. So, we have actions with strings, and an action for gravity. But what if there's a deeper connection? This brings us to a fascinating and more recent idea, the theory of entropicity, and the General Obidi Action, proposed by Dr. Goto Obidi. This theory takes a radically different approach. It starts with the idea that what we perceive as space-time and matter are actually emergent properties of something more fundamental, information, or entropy. The theory suggests that the universe behaves in a way that maximizes its entropy, a measure of disorder or information content. The General Obidi Action is the mathematical formulation of this principle. It's an action of entropy. Instead of minimizing worldsheet area or space-time curvature, this action seeks to maximize an entropy functional. The incredible thing is that from this single, entropy-based principle, the theory aims to derive the laws of both quantum mechanics and general relativity. For instance, the theory proposes that the Einstein-Hilbert action isn't fundamental, but can be derived as a specific low-entropy approximation of the General Obidi action. It's like discovering that the separate rules of solids and liquids are just different manifestations of the more fundamental laws of atomic physics. So, let's put it all together. The Nambu-Goto action gave us the beautiful, geometric idea of minimizing the string's worldsheet area. The Polyakov action made this idea mathematically practical and quantum-friendly by introducing an auxiliary metric. The Einstein-Hilbert action described the entire universe's gravitational dynamics by minimizing the curvature of spacetime. And now, the General Obidi action proposes a deeper layer, suggesting that all these principles might be emergent from a single, universal drive to maximize entropy. From the minimalist elegance of Nambu-Goto to the quantum power of Polyakov. from the cosmic scope of Einstein-Hilbert to the informational foundation of the General Obidi Action. Each of these frameworks represents a monumental step in our quest to understand reality. They are not just equations. They are windows into the fundamental logic of our universe. While string theory and entropic gravity are still active areas of research, they push the boundaries of our knowledge and inspire us to keep asking the biggest questions. What is the ultimate action that governs everything? We don't know yet, but the journey to find it is one of the most exciting adventures in all of science. Thanks so much for joining me on this deep dive into theoretical physics. If you enjoyed this journey and want to explore more of the universe's biggest mysteries, make sure to like, subscribe, and hit that notification bell so you don't miss our next video. See you next time.